Hello everyone. We'll continue our discussion of the kinematics chapter, and we'll be starting today with the all important section on strain. Now you're all familiar with the concept of strain, having studied it since your +2 as well as in your first year. Uh, what we are going to do here is to build on those initial concepts, those fundamental concepts where we define strain to be the ratio between the difference between the final length and the initial length with the ratio with the initial length. So based on that fundamental definition, but posed within the framework that we have been developing till now in this kinematics chapter, we'll be able to generalize particularly the two-dimensional concepts of strain that you have been studying in your first year. So the plan is this: build on the fundamental definitions that you have learned since your +2, but within the current framework, and then to generalize the concepts of strain that you have studied in your first year. So first of all, what we do is to define something called the engineering strain. The definition of engineering strain. So as I just mentioned, we are going to build on the absolutely fundamental definition that strain is nothing but the ratio of two different lengths. First, the numerator being the difference between the final length and the initial length, and the numerator being the initial length. So the engineering strain will be depicted by this symbol epsilon E. So this is our symbol for engineering strain, and just as we had used this particular symbol for definition earlier in the context of the displacement vector, we'll again use it here. So this stands for the definition, the colon in front of the equal to sign. And within the context of our current mathematical framework, we are going to say that in the numerator we have the difference between the final length and the initial length in this form. So the absolute value of the d small x vector, it depicts the final length of the length segment under consideration, which is basically, if you go back to our previous diagrams, you can see that the d small x vector is nothing but this line segment p dash q dash, and the d capital X vector is nothing but this pq. So that goes in the numerator, and in the denominator we have just this d capital X vector. Okay, so this is the raw definition of the engineering strain. But there is a little bit of a problem if we have to actually obtain a useful expression from this, because you see, this definition, it involves the absolute values or the magnitudes of the two vectors, d small x vector and the d capital X vector. Now because these are the magnitudes of vector quantities, so their mathematical representation would definitely involve some sort of a square root. Now dealing with square roots is not very convenient. So what we are going to do is, instead of the magnitudes themselves, we are going to instead consider the squares of the magnitudes, and that will make our life a little bit easier. So we consider the squares of the magnitudes. Now, the small x vector magnitude, where you can immediately see that this is nothing but the dot product of the dx vector with itself. Similarly, the square of the magnitude of the d capital X vector is nothing but the d capital X vector dotted with itself. Alright, so in order to obtain some kind of a nice expression involving this engineering strain, what we'll do is we'll begin our mathematical manipulations starting from this one, the square of the magnitude of the d small x vector. So if we do that, what we are going to obtain is something along this line, that dx vector magnitude square is equal to this thing, and this is equal to you see, this is what I'm using here is I'm going back and looking at these expressions. So d small x1 is equal to this big thing involving the derivatives of u1. Similarly, I'll be using the dx2 here and the dx3 from here. So basically what I'm doing here is writing, so maybe this will be clearer if I write this as dx1 square plus dx2 square plus dx3 square. And what I have written till now here, this is just the d small x1 square. So I have to write the d small x2 square, and that will be this. Again a square over this. So this is just the d x2 square from here, and finally for the d small x3 square, what we have is d capital X3 plus this entire term involving the derivatives of u3 this time. Taking square over this. So this is a rather long expression. Now it may seem like not a very good idea to expand this, but and we're not going to do that explicitly over this lecture, but it will be useful to write down a somewhat compacted answer to this. So we are going to do that in our next slide. So the plan is like this, that we are going to expand all this out, not explicitly, but we are going to do that and collect the various terms. So even before expanding, you can imagine that we will definitely obtain d capital X1 square from here, d capital X2 square from here, and d capital X3 square from here, and those three things together, that will be just this d capital X vector magnitude square. So that's good, and the other terms also will end up giving us some sort of a nice symmetric expression. So without further ado, let us actually write down that expression in a nice compact representation. So we are again going to write this thing, but in a compact notation. So this is as I had told you, I'm going to get these first of all, but they together mean just this. In addition, I will obtain a number of other terms which I collect and represent in this fashion. So I'm going to use another set of symbols to reduce the length of the expression here. So this is capital E11. I'm going to write down the expressions for E11, etc. Down below. Plus some terms involving the crosses between the x1, x2, x2, x3, and x3, x1. So written in this form, it gives us some idea of the nice symmetricity of the situation. Of course, you understand that the actual expressions of this E11, E22, E33, E12, E23, which is here, and sorry, I need to write a dx3 here. Then comes the E23, and the E31 will come with this dx3, dx1. So all these expressions of the e's, they will be quite long, but written in this form, it is relatively compact. Okay, so now comes the big part, where E11 is equal to sorry, this should be a del u2 E22 is similarly del u2 del x2 plus del u1 again, but this time the derivative with respect to x2 So again, I emphasize that it is not by some magic shortcut that I am obtaining these expressions. We have to actually expand this big thing here, all these square terms here, and obtain these expressions. But in the interest of time, I'm not going through all those detailed steps. This time we take the derivatives with respect to x3, take the squares just as before. Okay, now we have the cross terms, the e12. So this is going to be interesting. So you see, we have del u1 del x2 here plus del u2 del x1 plus you please note that this term, it does not involve any second order derivative, rather it is the multiplication of two first order derivatives. Proceeding further, we have similarly for E23, we have the cross between 2 and 3, so del u2 del x3 plus del u3 del x2, and the rest of the terms can be easily written down as before. And finally for E31, we have del u3 del x1 plus del u1 del x3 plus the rest of the terms as before. So please note that in each of these terms, these are the nonlinear terms or the quadratic terms. Each of these, they involve the u1, u2 and u3, but it is in the denominator, the partial derivatives. Here we have the x1 x2 combination uniformly all over the terms, corresponding to this 1 2 here. Similarly, when there is 2 3 here, we have del x2 del x3 in the denominator in each of these terms. Similarly, when we have e31 here, corresponding to the 3 and 1 index, we have del x3 del x1 del x3 del x1 and del x3 del x1 here. Okay, so overall, it is important to note that the entire expression has been considerably simplified by writing these in terms of the various components of this E11. Okay, now So I think I missed a term here. So there should be a 2 here, there should be a 2 here, and there should be a 2 here. So this is something I wanted to mention while I was writing this E1 to E23 and E31. You see, although we have written these three terms, we have not explicitly written down anything for E21, E32, and E13. But you note from these expressions that had we written the E21, this would have been exactly this term. Just the order in which these various terms have been written, they would have been reversed, but that would not make any difference. Similarly, for E32, it would have been exactly this expression, just with the order of the terms reversed. And similarly for E13. And because we do not write those terms explicitly, but they are actually present, so because you understand that they originate from squaring these various terms here from the previous slide. So because we are not explicitly writing the contribution from E21, so we write a 2 in front of this with the understanding that this E12 solely captures the responsibility of the E21 expression also. Similarly, this 2 carries that responsibility for E32, and this 2 carries the responsibility for E13. All right. So in the next part of the lecture, we are going to see how this expression for the d small x magnitude squared can be utilized to obtain some very useful expressions. Thank you.